welcome to Module 2 of the Partner Practice Enablement Bootcamp for Windows Azure. This 8-module training series is designed to help Microsoft's partners build their skills around selling and deploying Windows Azure. In this module, we will look at networking for Windows Azure infrastructure services. Topics include enabling, securing, and load balancing network endpoints, hybrid connectivity options through virtual networks, and traffic distribution through Windows Azure Traffic Manager. Our instructor today will be Michael Washam. Michael is the current CEO and co-founder of Opsgility, an organization focused on Windows Azure training. Michael is also a Microsoft veteran with a wide range of experience across Windows Azure that we are pleased to bring to you through this training. So with that, let me turn the floor over to Michael. Michael?
Thank you for the introduction. Hello, I'm Michael Washam, and in this session you'll be introduced to networking for Windows Azure infrastructure services. On the agenda for today's session, I'll start the session off by discussing how external traffic is routed to virtual machines through input endpoints and go deep by covering configuration of the load balancer. From there, I will cover Windows Azure virtual networks. As part of the virtual network discussion, I will cover site-to-site and point-to-site hybrid connectivity. I will end the discussion by discussing Windows Azure Traffic Manager, which is a DNS-based load balancing solution that enables scenarios such as geo load balancing and failover. Let's start the discussion off with endpoints. All traffic from the public internet comes to Windows Azure virtual machines through the public IP address of the cloud service, which is also known as a VIP. Each cloud service has a public IP, and this IP does not change unless all of the virtual machines are either deleted or shut down at the same time from the portal or PowerShell. Shutting down or rebooting from within the virtual machine does not affect the cloud service IP. In order for traffic to reach a virtual machine, an endpoint must be configured for a specific port such as 80 for HTTP, 443 for SSL, etc. The endpoint can forward the traffic from the public port to a private port on one or more virtual machines. By default, there will be two endpoints created on a Windows virtual machine, Remote Desktop and Remote PowerShell. For Linux virtual machines, only SSH is open. During the provisioning process, you can remove them or add others as needed. Each virtual machine is also assigned a private IP address for internal communication between VMs. This IP will be assigned out of a pool defined by Windows Azure. If you want to provide your own IP pool, you can do that by defining subnets in a virtual network and deploying the virtual machines with the subnet you choose into that virtual network. Let's dig a little deeper and look at how input endpoint port forwarding works. To allow traffic to reach a specific virtual machine, you define an endpoint. Let's use Remote Desktop as an example. Since there's only one public IP address per cloud service, but you need to reach each individual virtual machine on port 3389, the solution is to create an endpoint for each virtual machine that listens publicly on a unique port and forwards traffic to the fixed internal port of the virtual machine. In this case, when traffic reaches public port 6510, it is then forwarded on to VM1 on port 3389. If traffic comes in on port 6511, it is forwarded to VM2 on port 3389. For this example, I want to compare the networking configuration for the three virtual machines we created in the previous session. Demo VM1 and Demo VM2 are deployed in the same cloud service. If I open the dashboard for Demo VM1, you can see the public IP address 22.99.20.153 for Demo VM1, and it's the same IP address for Demo VM2. Now if I switch over to Demo VMPS, it's a different public IP address because it's part of a different cloud service. Now if you'll notice, all of the virtual machines have different IP addresses for different internal IP addresses. Demo VM1 is .71.164.38 and VM2 is 71.20.82. So let's take a look at some of the endpoints that are configured for us. So if I open up Demo VM1 and click on the Endpoints button, you can see that I have two endpoints created automatically. The PowerShell endpoint, which is listening on public port 5986 and private port 5986. This was the first virtual machine created, so 5986 was available, so the portal allowed it to use that port. Now if I switch to Demo VM2, it can't listen on 5986 because Demo VM1 is listening. So the portal has configured 49806 to be the public port, which then forwards to the private port 5986. And Remote Desktop is 52650, which forwards to 3389, and Demo VM1 is 64927, which is forwarded to 3389. Now to step into this a little further, I can click Edit on this endpoint, and I can change this public port to be whatever I want as long as it's available. So if I wanted it to be 3395, I just change the public port, click OK, and it will update the virtual machine configuration for Demo VM1. So the update is complete, and now the new public port for remote desktop is 3395. Load balanced endpoints follow the same concept we just saw with port forwarding. The difference is multiple virtual machines can receive traffic from the same public port. In this example, VM1 and VM2 both have an input endpoint configured to forward traffic from port 80 to private port 80. However, they are part of a load balance set, which tells Windows Azure to distribute traffic in a round-robin fashion to the virtual machines. Load balance endpoints can be configured with health probes for an additional layer of high availability. The first health probe type I'll cover is a TCP health probe. When you create a load balance set, this is a default probe behavior. The load balancer will attempt a socket connection every 15 seconds on a private port for your endpoint. The load balancer is looking for a TCP ACK from the connection attempt. If the load balancer does not receive a reply in response to 2 probes, traffic is no longer sent to the virtual machine. The load balancer does continue polling looking for the response, so when that virtual machine is healthy again, it's automatically put back into rotation. HP health probes are very similar to TCP health probes. Instead of looking for a TCP ACK, the load balancer is looking for an HTTP 200 or OK. If it receives something other than an HTTP 200, 401, a 500, a timeout, etc., it takes a virtual machine out of rotation. Just like TCP, the load balancer does continue polling looking for a healthy response, so when the virtual machine is healthy again, it will automatically be put back into rotation. The HTTP health probe allows you to provide custom code in the form of a web page to determine the health of your application. This allows for a much more thorough test of the virtual machine's true health. You can configure health probes using the portal. For HTTP health probes, you specify the probe path. This is a URL for the health probe. As you can see, the probe does not have to be on the same internal endpoint as the load balance set. This means you can have an HTTP probe for non-HTTP based applications, even UDP, as long as there's an HTTP endpoint available that determines the health of the application. You can also enable TCP or HTTP-based health probes via PowerShell at provisioning time or after. In this example, we're going to use demo VM1 and demo VM2 to demonstrate how to configure the load balancer. I've already installed IaaS on demo VM1 and demo VM2, so we have a service load balance. First thing I'm going to do is connect over to demo VM1 and modify the default HTML file that IaaS installs, add the server name of the current server. And the reason I'm doing this is so whenever we hit this server with load balance via the browser, we can see which server is actually servicing the request. So this is demo VM1, and I'll do the same thing with demo VM2. Now the next thing I need to do is actually add a load balance endpoint. So I'm going to open up demo VM1, go to endpoints, and add, since there's not an existing load balance set, I have to start with a standalone endpoint. Change this to HTTP. And I'm going to check create a load balance set. Now on the next page, I can specify LB HTTP, and I want to change the probe protocol to be HTTP. Now for this demo, I'm just going to set it to isstart.htm, which is the default page that we just modified. Go ahead and press confirm, and this will add the endpoint to demo VM1. Now before I add demo VM2 to as part of the load balance set, this update does have to complete. Now that the update is complete, I can go and add that same endpoint to demo VM2. So this time I'll choose add an endpoint to an existing load balance set, give it the same name. Actually, this is the name of the endpoint, not the load balance set, and confirm. And now once this virtual machine has been added to the load balance set, we'll actually be able to test it and verify that both virtual machines are showing up in the load balancer. Now that the update has completed, we can verify that both virtual machines are showing up whenever we browse to the cloud service URL. Okay, so the first request is serviced by demo VM1. Now after we hit the load balancer quite a few times, we should see demo VM2 pop up as well. Ooh, I just saw demo VM2. Let's run it a few more times to see. Okay, so demo VM2 is part of the rotation now as well. Now the next thing we want to do is demonstrate how this looks behind the scenes from the log files perspective. So if I go into demo VM1 and I open up the logs and open up the IaaS web logs, should be able to see my request plus the load balancer's health check requests. So starting off, you can see a bunch of requests from the load balancer agent, and they're all being served with a 200. Scrolling down, all the way down, you can see still that everything is a 200. Now if I go and I delete this file, IaaS if I just delete it, eventually once the load balancer polls again, it should see that the file has been deleted and that the server will start returning a 404, and it'll take the load balance node out of rotation. Okay, so let's go back and see if the load balancer has detected that the page is gone. So look at the logs. and scroll all the way to the bottom. And we can now see that the load balancer is being served at 404. So demo VM1 should be taken out of rotation. So now, if we refresh the page, only thing we see now is demo VM2. So now if we wanted to add the node back, we can fix the problem by adding the file back to www.root and give it a few moments for the logs to catch up. So there should have been enough time for the load balancer to pick up that the file's back. So let's take a look. And now we are seeing the 200 again. So let's go back and see if demo VM1 shows back up in the load balancer rotation. Okay, so demo VM1 is back in the load balancer rotation automatically by Windows Azure. So in this demonstration, you've seen how to configure the load balancer, how to configure an HTTP probe, how to troubleshoot using the web server's web logs to validate that the HTTP probe is getting returned back at 200, or if it's 404 or 401 or whatever, you can validate and figure out what's wrong with your load balancing configuration. Access control lists allow you to secure access to an input endpoint based on the network location of the client. There are many scenarios for securing endpoints with ACLs. Securing access to remote desktop for your virtual machines to only a white list of IP addresses for administrators is a great example. It is very easy to modify the ACLs on the fly using PowerShell or the management portal to securely allow administrators access and keep your attack surface low. Connectivity between services is another good example. For instance, allowing access to a service hosted in a virtual machine such as SQL Server from a Windows Azure website, or for that matter, a website or application running on any external service in a secure manner is another very common scenario. You can set access control lists per endpoint with up to 50 access roles. Each rule consists of the remote subnet in CIDR format, whether the rule is to permit or deny the remote subnet access to the endpoint, the description of the rule so you have a useful reminder as to why the specific rule is in place, and finally the order in which Windows Azure will process rules. The lower the number, the higher the precedence to the Windows Azure rules engine. Just like the portal, you can modify the endpoint and add an access control list directly from PowerShell. This could be used as part of an automated deployment to ensure that whatever service you're deploying is secure at boot. It could also be scripted to allow an administrator remote access based on the changing location of his or her IP address. The set Azure ACL config commandlet is used to create the access control list configuration object that defines the rules in the order. The next set of code sets the access control list on the MS SQL input endpoint using the set Azure endpoint commandlet. The final example shows how to set the access control list on a load balanced endpoint using the set Azure load balanced endpoint commandlet. In this example, I'm going to show how to use the Windows Azure Management Portal to secure access to a remote desktop endpoint so only my local network has access to demo VM2. To test this configuration, I'll download the RDP file for demo VM2 to my local machine. So just to validate my configuration, I'm going to attempt to connect from my local machine, and I do have connectivity. So I'm going to copy this RDP file and put it on the desktop of demo VM1, and just ensure that I have connectivity from the cloud service IP address as well. So both areas can connect. So now I'm going to go back to the Windows Azure Management Portal, and let's modify the endpoint for demo VM2's remote desktop. So I'm going to highlight the remote desktop endpoint, click Manage ACL, and I'm going to add my first rule. So I'm going to allow local access, and in order to do that, I do need my IP address. So I'll use Bing, what is my IP? 96.226.226.148. So let's switch back over here, .148, and I'm going to make this a /32, which basically means only this one specific IP address. I'm going to make another rule, makes it simple. It says deny everyone else, and this will just be everyone else. Go ahead and click confirm, and now let's wait for this endpoint to be updated. As soon as the ACL on the remote desktop endpoint is updated, we'll try the exact same test, one from the local machine and one from the demo VM1 in the cloud service. Okay, so the ACL is updated. So now let's try to connect from my local machine, which is behind the 96.226.226.148 address, and I still have connectivity. Now if I switch over to demo VM1, which is coming from IP address of the cloud service, and try the same connection, I'm sent a deny. So there's absolutely nothing listening on the other end of the service. So if you're a hacker, you don't even know there's a service there. So now that you've seen how to add access control lists from the Windows Azure Management Portal, let's walk through the same scenario using PowerShell. So the first thing I'm going to do is select my subscription, and I'm going to run get Azure VM to ensure that I'm working on the right subscription. So you can see the 3 virtual machines that I have here. So I'll grab the cloud service name and create a variable out of it. And I'll create another variable for the virtual machine name that we're going to operate on. So now the next step is to create an access control list object using the new Azure ACL config commandlet. New Azure ACL config just creates an empty access control list. No rules of any kind are in this at the moment. So to add rules, I use the set Azure ACL config commandlet with the add rule parameter. And I'm going to add a permit rule with the remote subnet. And this is the same subnet that we added in the portal. Specify the order 1 and a description. Okay, so the next thing I want to do is add another rule to deny everyone. And I'll specify order 2 and dash description deny everyone else. And whenever I do pass this, I forgot I do have to specify the ACL I'm modifying. Okay, now the final thing we need to do is actually take this access control list that we just created and append it to the endpoint for the virtual machine. Do a little PowerShell magic here. Get Azure VM, specify the service name, specify the virtual machine name, and this returns back a configuration object for the virtual machine. And part of that configuration is the endpoint configuration. So I can set the existing endpoint that I know about, called remote desktop, and I'm going to change this just the ACL on it and pass that new access control list. So this modifies the configuration object from Get Azure VM by appending the access control list to the remote desktop endpoint. And then I'm going to call update Azure VM to actually call the Windows Azure API to update this access control list. So after a few moments for Windows Azure PowerShell commandlets to call the Windows Azure API, the access control list should be exactly the same as whenever we set it from the portal. So the operation completed, and at this point, still should not be able to access from the remote machine. I should be able to access from my local, which is what I'm testing now, and that does work. Now if I go to demo VM1, it still is denied. And from PowerShell, just like the portal, you can also see your current configuration. So if I remove all this code, except for the variables, I should be able to dump out the configuration to Get Azure Endpoint, and that will tell me all the current configuration. And you can see that my 3389, allow local admin access, deny everyone else, is there. And I can pipe the same output out to Get Azure ACL config, and it'll give me more details about the access control list. Now that we have learned how input endpoints and access control lists work to manage inbound traffic from the public internet, let us shift our attention to virtual networks. Windows Azure Virtual Networks allow you to create your own secure and isolated network in Windows Azure. You control the IP addressing scheme of your virtual network by defining an address space and allocating subnets from the space to deploy virtual machines into. Virtual machines deployed into a virtual network have stable, persistent, and predictable IP addresses. This allows for complex deployments such as Active Directory to run in the cloud. Virtual networks also allow you to deploy and specify your own DNS servers for these advanced scenarios. Virtual networks also allow you to extend your trust boundary beyond a single cloud service. Virtual machines in different cloud services, including web and worker roles, when deployed into the same virtual network, are allowed to securely communicate directly. Windows Azure Virtual Networks also provides the ability to extend your on-premises data center to the cloud through hybrid connectivity. This capability provides the networking on-ramp required to migrate existing line of business applications and other enterprise workloads. This hybrid connectivity model supports the development of new hybrid applications that run in the cloud but have access to secure services and data only available on premises through a secure IPsec tunnel. A site-to-site virtual network allows you to extend your on-premises network to the cloud. This configuration allows the network administrator to establish a secure IPsec tunnel between the local on-premises networks and the virtual network defined in Windows Azure. The process is relatively straightforward. The network administrator first identifies any DNS servers that should be automatically assigned to virtual machines at boot. These can be on-premises or virtual machines in the cloud that may not have even been defined yet. The network administrator then identifies local networks that will be allowed to route traffic to Windows Azure. While defining the virtual network, the administrator specifies the local networks and the VPN gateway IP address. After that, the virtual network in the cloud is defined, the address space and the subnets are defined. Once the network is created, the administrator must then go create the VPN gateway itself. The gateway is a set of worker roles that attempt to connect to the on-premises VPN device. Once the gateway is provisioned in the portal, the administrator must take the authentication key and configure the on-premises device to allow the connection. Microsoft provides configuration scripts for many of the devices to make the on-premises device configuration relatively simple. Point-to-site connectivity differs from site-to-site by allowing an individual computer to connect over a secure SSDP tunnel instead of configuring the entire network to network. The connection is secured by certificates. This scenario is perfect for prototyping hybrid applications without requiring the upfront time investment of the site-to-site network. development and test, and of course it's much easier to demo since it does not have the public IP address requirements of the site-to-site network. A point-to-site configuration can coexist with most site-to-site configurations in the same virtual network. You'll see an example of configuring point-to-site in a later session. For site-to-site connectivity options, Windows Azure Virtual Networks has a growing list of officially supported devices and software solutions, including the built-in routing and remote access service in Server 2012. Devices not on the official supported list likely will work as long as they have support for the protocols and encryption schemes on the slide. So let's talk a little bit about creating the virtual network itself. First thing you should know is to plan and deploy the network before deploying servers. Virtual machines are provisioned into an existing virtual network. While it is possible to move an existing virtual machine to an existing virtual network, it's not a simple process. When planning for hybrid connectivity, you should also enable site-to-site networking at the virtual network provisioning time. While you can update some of the configuration after it is deployed, it is a requirement to enable site-to-site at the initial provisioning time. Currently, only a single IPsec tunnel is supported per virtual network. Supporting connectivity between Windows Azure sites is possible, though, by routing traffic through an on-premises hub. The gateway created in Windows Azure has built-in high availability. When you create the gateway, there are two instances of the gateway role created. One is active and one is passive, ready for a failure. For availability on premises side, most VPN devices support redundant configurations for high availability. The routing and remote access service in Windows Server is cluster aware, so this is also a viable high available solution. Finally, before I start the demo, let's discuss pricing. The virtual network configuration itself is free. However, once you provision the gateway, the cost is 5 cents an hour or roughly $37 a month. Standard data transfer rates do apply for data crossing the tunnel. The SLA on the gateway on the Windows Azure side is 99.9%. And one thing I do want to point out, the point-to-site connectivity option is currently in preview, so there's not an SLA available just yet. In this example, I'm going to walk through creating a site-to-site virtual network using Windows Server 2012 routing remote access service. My on-premise configuration consists of two Hyper-V-based virtual machines, AD01, which is running Active Directory domain services, and RS server, which is configured with routing remote access service to forward traffic for the virtual machines of my local network to the internet. I have an external firewall configured to forward incoming UDP traffic for ports 4500, which is IPsec, and 500 IKE to the internal IP address of my RS server. I'm going to switch over to my RS server, and I'm in the Windows Azure Management Portal on the navigation element on the left pane. So I'm going to go ahead and click Create a Virtual Network. Call this Demo VNet. I'm going to place my VNet in West US and name the affinity group for the VNet accordingly. So Demo VNet AG. So next, I'm going to enter a DNS server. This is going to be a reference back to my on-prem DNS server, which is 172.168.0.2. And I'm going to configure site-to-site virtual private networking. For the site-to-site connectivity screen, this is the local network. I need to describe what the local connections that will connect to my public connections in Windows Azure. So I'll call this local network. And it needs to know the VPN device address. This is a public IP address of my firewall that has the two ports opened. So 96.226.226.148. Next, I need to add the address space for all the networks that are on my local network. So I'm going to say 172.16.0.0 and just make this a /16. And then I will add in the other local network address space, which is 192.168.0.0 and as well as /16. So this basically describes that all the IP addresses in 172 or 192 address space of my local network can communicate to the address space in the cloud that I'm about to create. So to define the address space in the cloud, I can allow selection of the default 10.0.0.0/8, and then I can carve that up into smaller subnets. So I can create an app subnet and make this a /24 if I wanted to, or however you wanted to carve this up. Since we are creating a gateway, I need to select a gateway subnet, and whenever the two gateway roles that spin up, whenever I go to create the gateway, their IP addresses are going to be allocated off of this subnet. So I'm going to go ahead and click the checkbox to create the virtual network. Once this network is created, I'll need to actually open the network up and actually click the button to create the gateway, because you actually don't start getting charged for this virtual private network until this gateway is provisioned. Okay, so the virtual network is created now. So I'm going to go in to the dashboard and click Create Gateway. And for routing remote access, we are required to create a dynamic routing gateway. So I'll go ahead and select that, confirm, and creating a gateway can take anywhere from 10 to 20 minutes. Now that the gateway is created, I'm going to go ahead and click on Download Device Script, change the vendor to Microsoft Corporation, and click the checkbox. This will download the script to the desktop, and it's called vpnDeviceScript.cfg. Now this device script, whenever you generate it from Microsoft, is actually a PowerShell script that will configure RS to connect to the Windows Azure Gateway. So I'm going to rename that device script to .ps1, and I'm going to edit it in the PowerShell ISE so I can run it to configure RS. So the very first thing I'm going to run is call set execution policy, and I'm going to say bypass, and this will basically tell PowerShell not to prompt you because the script is unsigned. So I'm going to go ahead and hit 5 and allow PowerShell to configure the routing and remote access service to connect to the Windows Azure Gateway. So while it's restarting the service, you can scroll down and see that the gateway IP address that was created for you is already embedded in the file. So this file is generated with the correct settings already. So we'll wait a few moments for the gateway to start, or for the routing and remote access service to stop and start, and then we'll go back and check the status of our gateway. And sometimes after you run the script, it can take anywhere from just a few seconds to all the way up to 5 or 6 minutes for the Windows Azure Gateway to recognize that it's connected. Once this is stopped, we'll refresh, and if it's not connected, we'll pause and wait for it to actually be connected. Okay, so the routing and remote access service is officially restarted. I paused for a few moments to allow the connection to happen. So you can see in the Windows Azure Management Portal Gateway settings that the network is connected. And if we go back to the RS server, you can see that there is a new domain dial interface set up, and its connection state is also set to connected. So the next thing I want to do is to create a virtual machine and deploy it into this virtual network. So in Management Portal, I'm going to go to New Compute, Virtual Machine, select from Gallery, and I'm going to select Windows Server 2012 R2 Data Center, and I'll call this VNet VM, just so I know it's connected via VNet. For a username, and specify a password. So the next screen is where I have to specify the cloud service, and VNet VM cloud service name is apparently not taken, so I'm going to go ahead and put VNet VM service on there just so I can differentiate between the two. And I'm going to specify the demo VNet virtual network and the apps subnet that I created earlier. And now once this virtual machine boots up, it should have connectivity back to my on-prem Hyper-V environment, and I can join it to the domain, ping across the network, etc. So we'll go ahead and pause the recording for a few minutes to let this virtual machine provision up. Now that the virtual machine is up and running, after a short pause, I'm going to go ahead and connect to this and pick my user account that I created for it. And once I'm logged into the machine, I'm going to validate that we can indeed connect back over to the tunnel by trying to ping the Active Directory domain controller, the 172.16.0.2, which runs on my local network in Hyper-V. And once that's validated, then I'll actually try to join the domain to complete the hybrid connection. Okay, so the virtual machine has been provisioned all the way, so let's validate that I can indeed ping back to my on-prem virtual machine. So I'm going to ping 172.16.0.2, which is the on-prem domain controller, and I can ping that. Now I'm going to switch to the domain controller and try to ping back to this virtual machine. So this virtual machine booted up with an IP address of 10.0.0.4. So I'm going to ping 10.0.0.4. And you notice I cannot ping. And the reason is not because we do not have connectivity, but by default, virtual machines in Windows Azure do not have ICMP enabled. So I'm going to go ahead and launch the administrative tools, go into Windows Firewall with Advanced Security, and enable ICMP. So I'll go to Inbound Rules, File and Printer Sharing, Echo Request, and make sure it's for IPv4. Okay, so now I should be able to ping this machine from on-prem. Okay, so now we've established ping works. So let's go to and actually join the domain. Go to System, change settings, and change to my on-prem domain. So this will be contoso.com, and it should reach out to via DNS that I configured in the VNet. And I can specify username and password, click OK, and it should reach out over the tunnel, connect to domain controller, make sure that this computer name is available and it's valid and the credentials are good. And once all this validation has taken place, I should get a pop-up that says welcome to the Contoso domain. And there it is. So go ahead and click OK, and this is the end of the demo. Essentially, you've seen how to establish a virtual network using Windows Azure, configure a site-to-site tunnel, configure a DNS server for any virtual machines that boot up. They'll automatically have this DNS server. This allows you to have domain join capabilities back on-prem, or if you wanted to, a domain controller in the cloud. Windows Azure Traffic Manager is the final piece of the networking puzzle for this session. Traffic Manager recently has went into general availability and is fully supported with Windows Azure Virtual Machines. So what exactly is Windows Azure Traffic Manager? Traffic Manager is a DNS-based load balancing solution that is designed to globally distribute traffic between geographies. It supports 3 different load balancing algorithms: performance, round robin, and failover. To set it up, you create a Traffic Manager configuration, which gives you a Traffic Manager domain such as contosotm.trafficmanager.net. Then map the parent domain that you want to load balance to the trafficmanager.net domain using a CNAME. You then associate the Windows Azure Cloud Service endpoints up to 100 that should be load balanced to the Traffic Manager configuration. Traffic Manager also supports HTTP health probes just like Windows Azure endpoints. Specify the HTTP page during configuration creation that Traffic Manager will use to determine endpoints availability. The performance load balancing algorithm works by determining the fastest route for the client and then returning the correct IP. For example, a client coming from Portland, Oregon, Traffic Manager will calculate the hops between endpoints and user. Traffic Manager will respond with the IP address for the closest data center location, and then the client makes a request with the result IP. The round-robin load balancing algorithm just returns the IP address from the next data center regardless of the client's location. For example, a client coming from Portland, Oregon, Traffic Manager returns the next IP, could be east or west. Traffic Manager sends the IP to the client, and the client makes a request with the resolved IP. The failover load balancing algorithm returns the IP for the primary site unless there is an availability issue. If that happens, it will return the endpoint from one of the other endpoints in the failover order that you specify. For example, the client requests contoso.com. Traffic Manager responds with the IP for contosowest.cloudup.net. Client makes a request with the resolved IP. The service in the West US goes down. The next request comes in. Traffic Manager responds with the IP for contosoeast.cloudup.net, and the client makes a request with the resolved IP. In this demonstration, I'm going to walk through creating 2 virtual machines, one in the West US data center and the other in the East US data center. From there, I will enable Windows Azure Traffic Manager to distribute traffic between the 2 virtual machines using the failover load balancing method. So my first step is to create the 2 virtual machines. So I'll create one for the East. Let's call this East VM1. And I'll go ahead and pick the East US data center. And since I'm going to load balance, I'm going to use HTTP to be the load balancing method. So I'm going to go ahead and open up at that endpoint now. So while this machine is created, I'm going to go back and create the West VM1 virtual machine. Enter username and password, and now I'm going to pick West US for the virtual machine location. Just like before, I'm going to add the HTTP endpoint. And go ahead and click OK. Now, before we can proceed configuring the virtual machines for load balancing, we do need to wait for them to be provisioned, so I'll go ahead and pause the recording for a few moments. Now that the virtual machines are both booted up, I need to log into both of them and install IaaS to configure them so we can test for load balancing. So I'm going to log into the first virtual machine, and while it is loading up, I will log into the second virtual machine. Now that both virtual machines are booted up, I'm going to open up each one of them, start PowerShell, and install IaaS. So that one is starting to install. Let me do the same thing for the one in the West US data center. Okay, so now that that is starting to install, go ahead and pause the video again until they're both completed. Now that IaaS has been installed on both virtual machines, I'm going to edit the IaaS start page to show which data center we're actually operating the virtual machine from. So just like one of the previous demos, I'll open up IaaS Start in Notepad and put the data center location in the actual HTML. So this one will be East US, and the other one, of course, is West US. So add the data center location in the HTML and we'll be good to go. Okay, the next step is to create a Traffic Manager profile. So I'll go to New, Network Services, Traffic Manager, Quick Create, and I will call this PP Demo Traffic Manager 1. It does have to be unique because it's going to be part of the .trafficmanager.net namespace. And for the load balancing method, I'm going to go ahead and create this one with failover. Let's go ahead and click Create. Alright, so the Traffic Manager profile has been created. Let's open that up. First of all, let's go to Endpoints, and we can add the 2 endpoints that we just created, East VM1 and West VM1. Go ahead and click OK. And now Traffic Manager is reaching out to check the actual endpoint status to make sure everything is okay. Now that the endpoints are online, let's take a look at the configuration real quick just to see how things actually work. So if I flip over to the Configure tab, you can see that the DNS name, this is the main DNS name that Traffic Manager uses to route traffic, is ppedemotm1.trafficmanager.net. The DNS time to live is set to 300 seconds by default. The load balancing method is right here, currently set to failover, And the failover priority list, eastvm1.cloudapp.net, is the first endpoint that should generate the traffic. So you can see that we can also specify the monitoring settings, specify /IaaS start if we wanted to, or /health check, whatever we need to do to actually make sure that there's going to be an HTTP OK return back to Traffic Manager so it knows whether that node is online or not. So let's go ahead and take the DNS name and browse to this and make sure that we get a proper response. So you can see at the very top, probably tiny, but it's East US, so you can see that yes, Traffic Manager is working. So now what we want to do is to validate that failover does occur. So I'm going to go back over to my virtual machines, and I'm going to shut down EastVM. So as soon as EastVM has shut down and the DNS time to live has went away, this is not an instant failover because this is DNS, then we'll go ahead and refresh our local DNS cache and try to hit that main URL again and see that we did fail over to a West US server. Now that the virtual machine is shut down and we've waited a few moments during a pause to allow the DNS to time out, let's go ahead and refresh the local DNS cache. Okay, so now whenever we make a new request, we should ask for a new IP address from DNS, and Traffic Manager should now give us a failover version. So now you can see that West US is our failover, and if we go back to the portal and scroll down to Traffic Manager and look at the profile, we should see that endpoint is now offline or degraded. And it is. So it detected that the virtual machine in East US was down, and it failed over to the alternate West US virtual machine, and DNS has since been updated. So one thing to keep in mind, this is a great solution for geo load balancing and geo failover, but it is not foolproof. Obviously, these virtual machines were serving in a real application. There would have to be data synchronization of some kind going on behind the scenes. Windows Azure SQL Database has a great replication engine that allows you to replicate databases between services, but other services likely would need some manual intervention and some manual replication built to ensure that they could work. In this session, we discuss Windows Azure endpoints, how to create them, how to configure load balancer settings, TCP and HTTP health probes, and how to secure access to them using access control lists. We then moved on and discussed virtual networks, including configuring hybrid connectivity with site-to-site and point-to-site networking, and the session ended with Windows Azure Traffic Manager, which allows you to distribute traffic globally between Windows Azure data centers. Here are some of the suggested learning exercises to learn more about the technologies discussed in the session. For a deeper dive on these topics, I suggest the resources in this slide and the next as well. Finally, here are some really great resources for Windows Azure in general. Coming up next, the next session will explore Windows Azure Active Directory. And thank you very much for watching the session.